In the next 3 hours, with a little break in the middle, I'm going to try to give you an introduction to machine learning. And obviously, machine learning is a huge field, and this is going to be just some very basic stuff, which I think everybody should know. And then maybe if we get to it at the end, some teasers for more interesting things. And here is a promise. I have 6 lectures to squeeze into 3 hours. I have planned it so that there is no way I will ever possibly be able to make those 6 lectures, but the promise is that all the other material in the sort of last 2 lectures or so, I'm happy to present at some later point in the future. Okay, so first of all, I want to get a sense for how exposed people here are to machine learning. If you have used logistic regression, raise your hand. Okay. If you have not used logistic regression, raise your hand. Okay. If you know the backpropagation algorithm, raise your hand. Okay. If you have not, do not. Okay, good. Have you ever used Markov chain Monte Carlo methods? Smaller number of people. And have not? Okay, good. So this lecture is fine. Some of you will be bored, but at least you'll only be bored for 3 hours. Some of you will hopefully learn new things. All right, so let me jump in. Machine learning is a big buzz phrase these days. It's related to many other terms. Artificial intelligence, statistical modeling, neural networks and deep learning, data analytics. Oh, I have data science on there. Oh, that's good. Data science, pattern recognition, data mining. These are all related terms. They live on some continuum depending on what community you live in and what kinds of data analysis you sort of do, and whether you're trying to build brains or you're trying to, just analyze some data somebody gave you. Okay? So machine learning is related to all these terms. It's related to many traditional academic fields as well. So if you ask yourself, where does machine learning normally sit in a university? I would say normally it would sit in computer science, but actually many statistics departments are hiring people doing machine learning. I happen to sit in engineering. We use a lot of tools for applied mathematics. We get inspiration from economics, from computational neuroscience, from cognitive science, and there are even people in physics who do machine learning. So there are many related fields, which makes it actually really exciting because people interact kind of like the ATI. We learn from each other and we advance the field. And there are many, many applications. So the way I kind of think about it is that machine learning is a sort of invisible substrate over which many other things are possible. So, areas traditionally like robotics, computer vision, and so on that are related to AI depend on machine learning technology. Language processing is essentially heavily using machine learning. Also areas of the sciences, so bioinformatics, scientific data analysis uses a lot of tools for machine learning. In the commercial world, recommender systems, translation systems, advertising, finance, etc. Okay? Many, many applications. And I'm going to go into this in a little bit more detail just to motivate people. Again, I will not spend too much time on this. I'll go very quickly. You can always watch the video at half speed or something like that if you want later. So here's my attempt at defining machine learning. It's an interdisciplinary field that develops both the mathematical foundations and practical applications of systems that learn from data. And if you want to know more about machine learning, then you need to be plugged into the machine learning community. And the machine learning community is very heavily dominated by conferences where all our best publications happen. These are peer-reviewed conferences. NIPS, ICML, AISTATS, UAI, and sort of slightly more data mining like KDD are sort of the main conferences. And then we also have some journals where we tend to publish, after we publish in the conferences, longer versions explaining all the details of stuff. So JMLR, IEEE, PAMI, and a lot of the statistics journals. So it's different from most typical fields of science where conferences dominate over journals, and conferences are very heavily peer-reviewed. Okay, so that's the field, and let me just zoom through a whole bunch of applications so you get a feeling for why you might want to spend the next 3 hours paying attention. So we're in an information revolution. Data is everywhere. It's transforming society, the sciences, and the business world, and we need tools for modeling, understanding, predicting, and decision-making from large data sets. That's kind of, this slide could capture part of the mission statement of the Alan Turing Institute. And machine learning is motivated by the same thing, this information revolution. Let's talk specifically about some of the applications. So things like automatic speech recognition, machine translation, dialogue systems. These are all based on applying machine learning methods to speech signals and transcribed speech. Computer vision, things like object face, handwriting recognition, image captioning. This is a very old image from Jan LeCun of applying some computer vision methods to recognizing objects a bunch of years ago. And it's sort of doing okay, plane. This dinosaur is recognized as an animal, that's recognized as a truck. Things have moved on in the last few years. This is a nice example of image captioning, where you give the computer this image and it comes up with the text. This image is never seen. It comes up with the text, man in black shirt is playing guitar. Construction worker in orange safety vest is working on road, etc., etc. Okay, this is not quite accurate. Doing backflip on a wakeboard, well, that's a trampoline by the water. Okay, you can excuse the computer for getting a little confused there. Okay, now, this is cherry-picked. This is from one of the papers. It's a very impressive paper, but you have to always take these things with a grain of salt. It's not the case that computers can look at images and come up with wonderful descriptions of what's happening yet, but these are some very impressive examples of what's going on. Face detection. Have you ever wondered how that little box appears on your cameras or phones? Well, that's a machine learning algorithm that's detecting faces and putting a little box around them. Very standard now. We almost take it for granted. Now, in the sciences, we have scientific data analysis. This is a picture of a gene expression microarray. This is a picture of a robot scientist. That's not the robot scientist. The thing behind him is the robot scientist. And these are sort of methods for analyzing data and making predictions about scientific data and using those to design new experiments so as to improve experiments and so on, and help with the scientific endeavor. And the thing is that scientific data is exploding in size, and we really need computers to help us understand what's going on, and machine learning methods and data science methods are useful for that. Recommender systems, we all know that when we go shopping for things, we're now often, if we're online, we're always given some recommendations for what else to buy. That's driven by machine learning methods. Autonomous vehicles, this is a big deal these days. This is the Google self-driving car. Uber has some cars out in Pittsburgh. In case you thought this was all new, this is from the late 1980s. This is Alvin, a self-driving car driven by a neural network like that around Pittsburgh, and driving at 70 miles per hour on highways. That must have been very, very scary in the 1980s, because I'm sure it was like doing crazy things. But autonomous vehicles have been in people's imagination. Now they're becoming a reality. A lot of what drives them is better machine learning algorithms. Robotics, again, a field driven by machine learning. Computer games, you've seen these, beautiful examples of the stuff that DeepMind next door is doing on, for example, learning to play a number of Atari games at superhuman level, learning to beat the world master at Go, etc. again, all driven by machine learning algorithms. Right. Automated trading, another area that's very heavily using machine learning. Some places more than others. It's quite difficult to get people to use machine learning in settings like that, but actually some hedge funds and banks are using machine learning. Okay, so the goal of these lectures is to introduce some very basic concepts. Even if you've heard about them, like logistic regression, I want to reintroduce them to you so that you can see the connections to everything else. Okay? There's much more on this topic. And I've given you 4 links that you might want to follow. One of them is if you go to video lectures and you just search for machine learning lectures, there are 3,500 of them. So that's not very useful. So you search for any particular topic you want to learn about. You'll find either a talk given at a conference or a tutorial given at a summer school. Those are more useful. The latter are more useful for learning something. This is a fantastic resource. There are entire machine learning summer schools on video lectures where all of the lectures are there, and so you can learn about almost any topic in machine learning that way. At Cambridge, we teach a class called Probabilistic Machine Learning. You can look at the syllabus of that if you're interested. All our material is online. Coursera was founded by 2 machine learning researchers, so it's no surprise that this MOOC has a lot of machine learning material. And Andrew Ng's machine learning class has been taken by hundreds of thousands of people. I think it's excellent, but you know, there's a lot out there that is not covered necessarily in a course like that. And then there are excellent textbooks by various people: Kevin Murphy, Chris Bishop, David Mackay, Hasty, Tiprani, Friedman. That's just a short list. Okay, so let's go through some basic concepts and terminology that you might come across. So imagine you have an organism or machine. Now, the nice thing about machine learning is that the concepts, the sort of theory of systems that learn, apply not just to artificial systems, but they also apply to biological systems. So they inspire people in neuroscience and cognitive science to think about organisms. So I'm not going to really make a distinction. We're all machines. Okay, so imagine a machine which experiences a series of sensory inputs. And these sensory inputs are going to be called, say, I use the pointer, x1, x2, x3, x4 over time. All right? Now, in supervised learning, the machine is also given some desired outputs, so y1, y2, etc. And its goal is to learn to produce the correct output given a new input. So for example, the machine might be given examples of images and text labels for the images, and its goal is to learn the mapping from the pixels in the image to the text label. All right, that's a classic supervised learning example, and many of the breakthroughs in machine learning are just massive brute force supervised learning on huge data sets. Then there's unsupervised learning, which is actually quite a lot more interesting, and the goal is a little more difficult to describe here. So the goal of the machine is to, I would say, build a model of the data. It's not given any desired outputs or targets. It's just given data. So what do? You could just ignore the data and you'd be fine, right? But actually what the machine ends up doing is, in unsupervised learning, is it's building a model that discovers structure in the data. And then it can use that model to do reasoning about the data. It can do decision making if you give it a loss function. It can predict things about the data, like maybe the next sequence or missing parts of a particular input. It can communicate the data efficiently by having a model. You can compress the data into a few bits and communicate it, etc. And then there is reinforcement learning, where the machine can also produce some actions. Okay, call them A1, A2, etc. And these actions affect the state of the world that the machine is in. So, whereas in these two, in a sense, we're thinking of the machine as somewhat passively taking in data, in reinforcement learning, this machine is an agent in the world. It's taking actions, or you could call them decisions or control outputs or whatever you want to call them, and these affect the state of the world, and then the machine isn't told what its ideal actions should be. It's just given a reward or punishment. Okay? So that's usually a scalar symbol, signal, R1, R2, etc. over time. So every time the machine does something good, it's given a reward. Every time it does something bad, maybe it's given a negative reward or a punishment. And the goal of the machine is to learn to act in a way that maximizes the rewards in the long term. Okay? It interacts with this world and is trying to not maximize its immediate rewards, but the rewards in the long term. So any questions about this so far?
How common is the third one?
How common is the third one? Well, depends on the application. So let's take an example, like image recognition. What do you think that is? Sorry? It's the image recognition would be something like supervised learning. Usually the way you train them is you give an image and you give it the label or something like that. Whereas game playing, things like building an agent that plays Go or Atari or something like that is generally phrased as a reinforcement learning problem. These things are not entirely clear-cut. There are some fuzzy boundaries between these things. So for example, when you're doing reinforcement learning, you can heavily use supervised learning and unsupervised learning to help you. DeepMind's AlphaGo system certainly did use a lot of supervised learning as well. Yep.
So can I think about reinforcement learning as also something like semi-supervised learning?
Semi-supervised learning is in lecture 6, which is things I won't, the title of lecture 6 is things I didn't have time to cover. Okay? And I've done a lot of work in semi-supervised learning. I'm happy to talk about semi-supervised learning. Semi-supervised learning, in a nutshell, is when you have lots of unlabeled data and a little bit of labeled data. So for example, imagine you have all of Flickr, all images on Flickr, and somebody has carefully labeled 1,000 images. That's a perfect semi-supervised learning example. You might have 100 million unlabeled images and 1,000 carefully labeled images. And the question is, how do you combine unlabeled and labeled data to perform best at labeling future data? That would be semi-supervised learning. Okay. Other questions?
When you say desired outputs Y, that's normally just a bit, right? Or a category, not necessarily a structure to it.
No. That includes structure. So imagine that your input is an image, and your output is, for every pixel in that image, a label for the category of that pixel. So your input is 1,000 by 1,000, and your output is 1,000 by 1,000 as well, with different discrete labels for every pixel. And those are structured. That's a structured output supervised learning problem, but that's still supervised learning. It's quite, once you understand this stuff better, then actually these distinctions become more fuzzy. Other questions? All right.
Do you always know the output space?
It's usually in the problem definition, but actually some interesting problems might have open output spaces. So for example, you might have discrete labels, but you might not know how many you have. And one can define problems like that as well. All right, so 3 types of learning. Good terminology to know. All right, so now over the next few lectures, and these are just bits of my 3-hour chunk, I'm going to cover the following 4 topics: classification, regression, clustering, and dimensionality reduction. And for what I'm going to describe, we're going to use extensively some basic concepts in probability statistics, calculus, and linear algebra. And when I mean basic, I mean kind of like high school, advanced high school to early undergraduate for most of these things. Some of the maybe combinations of calculus and linear algebra are, advanced undergraduate. Okay? But it's important to know these things. So I'm just going to lay out a couple of these things, but you'll see that towards the end. So let me just go through this, these different canonical problems in machine learning. So classification. So classification, we're going to assume that we have some data. For simplicity, we're going to represent the data by vectors in some vector space. Okay, this could be, a data point x is going to have some elements, x1 through xd. For example, if the data point is an image, the elements would be the pixel values, intensity values for its d pixels. Okay, if x is a document, we might represent the document as the frequency of all the words in the vocabulary. There are many ways of representing things, but for the purposes of this, I'm just going to assume that our data is represented somehow by a vector of numbers, a sort of a long string, a collection of numbers. Okay, so an element of x, x sub d, represents measured or observed features of data point d, however you got them, and big D denotes the number of measured features of each point, the dimensionality of the data. And now a data set, I'm going to use calligraphic D to denote data sets, consists of n pairs of data points and corresponding discrete class labels. We have pairs, x1, y1, and this is the input data, and that's the class label. And that's our training data that we're going to learn from. And in classification, we're going to assume that the label is one of C classes. So for example, we might have, images of objects, and we might have 1,000 different categories of objects, and so Y would be some discrete label in 1 through 1,000. And our goal is to classify new inputs correctly. In other words, to generalize. We're not just trying to memorize our training data, we're trying to learn something from our training data so we generalize well to new data. So here's a little canonical example of this. We have our points in one class and our points in the other class, these red X's and the cyan O's. And here, that might be our classification boundary that classifies reds from cyans. And a new data point here would be classified as cyan in that classification boundary. So examples of this are classifying spam versus non-spam email, normal from diseased tissue, or digits in a digit classification task. Questions about that? Very basic. I'll spend a whole lecture on that soon. Okay, here is a very classic example. I like using this because this example comes from 1935. Some person called Anderson collected properties of flowers from the iris species. And there are sort of three iris species, Setosa, versicolor, and virginica. And Anderson collected 4 attributes of these plants. He did it for 150 plants. There's an iris for you. And a year later, this was used by Fisher, one of the founders of the field of modern statistics, to define essentially the first modern classification method, Fisher's linear discriminant analysis. Okay? So very important historical data set. And here's the data. The data looks like this. There are these 4 numerical attributes, and then there is the class label as the 5th column. Okay, and there are 150 data points. N equals 150, D equals 4, and there are 3 classes. So C equals 3. And if we look at 2 of these properties plotted here, we can see, one of the classes clearly separated from the other 2. And we can also see all sorts of other interesting things, like the fact that the data was discretized to within 0.1, and so on and so forth. Okay? So is it pretty clear what this problem is? So essentially, if you build a classifier for this, when you get a new data point, you'll be able to classify it as one of these 3 different types of iris. Okay. Now let's talk about regression. So here is regression. Now, again, we're going to have data that's going to be some vector in d-dimensional space. So this bit is the same. And now again, we have n pairs of inputs and outputs. Except that our outputs, the y's, instead of being discrete class labels, are going to be real numbers. Okay? So y is a real, and our goal is to predict with some accuracy the output given a new input. And a canonical example of regression, which I'm going to use throughout these lectures, is fitting polynomials to data. Here we have, 8 data points, and we can fit the constant polynomial, linear, quadratic, cubic, quartic, quintic, etc. That's a regression problem. Y is continuous, and in this case, x is one-dimensional, but we can easily generalize it to multiple dimensions. Any questions about this? Classification and regression, what kind of learning are they? Supervised, okay? All right, clustering. So given some data, the goal of clustering is to discover clusters of points. Okay, that's a bit circular, so let me unpack that. Roughly speaking, 2 points belonging to the same cluster are generally more similar to each other or closer to each other in some sense than 2 points belonging to different clusters, right? It turns out that clustering theoretically is very hard to define. Different people have different criteria for clustering. We're going to define a particular classical clustering algorithm, and we're going to study that in a little bit of detail. So examples of this might be clustering news stories into topics, or clustering genes by similar functions, something that people in bioinformatics do quite a lot, clustering movies into categories of movies, or clustering astronomical objects as they come in a telescope. And here is a canonical picture of clustering. Our data are the blue dots, and the output of the clustering algorithm is something like the definition of these 6 different clusters, which have a center and some spread. Okay, and this is in particular clustering using a Gaussian mixture model, but that's a detail. Okay, so now clustering, what do you think clustering is? What kind of learning problem do you think clustering is? Unsupervised. Because we're just given data, we're not told what the labels are, and it's supposed to find structure in the data. Okay? So dimensionality reduction, given some data, the goal is to discover and model the intrinsic dimensions of the data, and or to project high dimensional data onto a lower number of dimensions that preserve the relevant information, whatever that is. Okay? And the insight of dimensionality reduction is that our data, when we measure it, might be very high dimensional. For example, if I take a picture with my camera, the dimensionality of the pixel space that we get out is millions, right? Millions of pixels, each of them have a red, green, and blue value, so, multiply that by 3. However, if I take a picture of somebody's face, there might be only some number of degrees of variation in the space of natural faces. And this, I think the nicest example of this is this somewhat artificial example, which is, imagine I took pictures of a statue from different angles and with different directions of illumination. Okay, so I have a statue, and I can take pictures from, let's say anywhere on a sphere, maybe moving further away and towards the statue, so maybe there's 3 degrees of freedom in terms of the direction of taking that picture, and if there's only one illumination source, there might be 2 degrees of freedom in that. If there was an illumination intensity, there might be 3. So there would be probably 6 underlying dimensions to the space of all pictures of this statue that I could take. Even though I might be measuring 1 million pixels, the data lives on some 6-dimensional manifold. And so this is kind of indicated by diagrams like this, where you have a lot of data and it lives on some low-dimensional manifold in some high-dimensional space. It's very hard to plot this because, I can't plot more than 2 dimensions on the screen. Okay, so that's dimensionality reduction, trying to discover that underlying dimension. Okay, so a bit of background, and of course you have all this material so you can look at it later if you want. We're going to use probabilities. Why are we going to use probabilities? Well, we're talking about data. We sample data. Data comes from some distribution. We try to build models of data. The language of modeling is probability theory. We're trying to make predictions. We're uncertain about our predictions. The language of uncertainty is probability theory. Okay? So probability is really fundamental to everything in data science. So a bit of boring stuff. We're going to have random variables, and probabilities are non-negative, and they sum to 1 or integrate to 1. And we have some terms that are useful to know, things like the joint probability of 2 random variables taking on some values, which is written with a comma. So it's the joint probability that variable x takes on value little x and variable y takes on value little y. Say, for example, the joint probability that it's raining at the same time in London and Paris. Okay, that would be an example of that. Then you have the marginal probability of x, which we write like this, which is the sum over y of the joint probability. So the marginal probability that it's raining in London is the sum over whether it's raining or not in Paris of the joint probability of rain in London and rain or not rain in Paris. Okay, you sum out the other variables. And conditional probability is written like this. Now I'm generally going to drop all this like big X and little x stuff because it's a nuisance. So conditional probability is going to be written x with a vertical bar y, which turns out to be the joint probability divided by the marginal probability. And that would be the conditional probability of, say, rain in London, given that it's raining in Paris at the same time. Okay? Now, in probability theory, there's basically 2 rules that you need to know. The sum rule and the product rule, which is sort of written out here. Sum rule says the marginal probability is the sum or integral over other variables of the joint probability. And the product rule says that the joint probability can be factored into a marginal probability of x times a conditional probability of y given x, or the other way around. And from those 2 rules, we get a corollary, which is called Bayes' rule, which tells us how to transform conditional probabilities of x given y into conditional probability of y given x if we know the marginal probabilities. Okay? A simple corollary of the sum and product rule. And this is the stuff that we're going to use a lot. This is at abstract level, but to apply this, we need to actually know about some probability distributions, and there are as many probability distributions out there as you choose to invent, but some of them are very widely used for good reasons. So things like the normal distribution, written here, the multivariate normal distribution, which is the normal distribution in d dimensions, so normal or Gaussian, right, is hopefully familiar to a lot of people. This is sort of giving you the bell-shaped curve. This is a bell-shaped bump in d dimensions. The Bernoulli distribution for binary random variables, which tells you that the probability of the binary variable being 1 is theta, and the probability of it being 0 is 1 minus theta. A generalization to discrete variables, known as a discrete categorical distribution, which can be written like this. If you have L discrete class labels, for example, uniforms, gammas, betas, Dirichlet's. I'm not going to go through all of these. I put them here because I might refer to them, and you can look them up on the slides or on Wikipedia or whatever. I'm not going to, this is a pretty picture of Dirichlet distributions, which I'm not going to talk about. A very useful thing to know is that a lot of the commonly used probability distributions belong to something called the exponential family of distributions. And the exponential family of distributions is all probability distributions that can be written. This is a probability distribution over x, given some parameters theta. These probability distributions can be written in the following form. They're a product of some function of x, some function of theta, okay, no interaction between x and theta here, And the only interaction between x, the data, and theta, the parameters, is happening inside of an exponent through something called the vector of natural parameters, so you can transform theta in some way, and something called the sufficient statistics, and these guys are interacting linearly inside an exponent. So this sounds very abstract, except that once you look it up, you see that you know, a lot of things that we use, like the binomial, Bernoulli, Gaussian, multinomial, Poisson, etc., are members of the exponential family. Okay, just something to know about. And there's a lot more to know about. I put a crib sheet that we use in our course here, which covers some of the basic linear algebra, calculus, and probability theory that you need to know, and a very nice pattern recognition glossary that's now a few years old that Tom Minka put up several years ago. So that was the end of lecture 1. Do we have any questions? Not much to ask questions about yet, right? How are we doing on time? 40 minutes? Everybody still has some energy? Okay. All right. Okay, lecture 2, regression. All right, so a very basic topic in statistics and machine learning. So this was the picture I had for you before. I don't need to explain it again. We have pairs of data, x's and y's, and we're trying to model y as a function of x by fitting curves to data, basically. And so let's imagine the simplest possible case. Instead of the multi-dimensional regression where x lives in d dimensions, let's consider 1D linear regression, all right? Now, some of you may be trying to fall asleep right now, but I urge you to pay attention because once we figure out 1D linear regression, the whole world of regression opens up to us, and we can solve all sorts of other interesting problems. Okay, so we have pairs of data, x and y, and everybody knows that a linear function is written y is ax plus b. So, is that a reasonable model? And my answer is no. It's not a reasonable model because what this says is y equals exactly ax plus b. And I challenge you to find any data out there in the world not generated by an infinite precision computer that matches that. There is no such data. That's not a valid model, okay? So, to make this into a model, we have to say something else. We have to say, well, what if it doesn't, okay? And that's what the noise model is. So what we're going to now say is y equals ax plus b plus some noise that's unknown. Okay, so that allows me to fit a linear regression where the line captures, you know, the pattern in the data, and whatever is not on that line is captured by this noise epsilon. That becomes a model. Now that's a model, okay? It could make forecasts about future data that are realistic. So epsilon n is a model for the noise, and now we have all sorts of freedom. We fixed ourselves to linear regression, but we have the freedom to choose different distributions for the noise. So what distribution should we assume for the noise? Any suggestions?
White noise.
Gaussian, yeah. White noise is, you know, uncorrelated Gaussian. Why? Because everybody else does it? Always ask yourself these questions. Modeling, you know, modeling involves assumptions. All modeling involves assumptions. All assumptions should be questioned. All assumptions should be clearly stated when you describe your model, so that other people can say, that assumption is wrong, I don't like that assumption, I have this other assumption. Okay, so we are going to stick to the Gaussian. And
that goes from signals and systems. Like everyone uses Gaussian noise because that's like the salt and pepper noise that uses. So it follows like.
yeah, but the reality of real data is that very rarely, except if you're dealing with thermal noise, very rarely do the discrepancies from your model have Gaussian structure.
But you can model the expected value if you have enough data to like adjust the noise.
Yeah, but that's not that's still you fit the line assuming Gaussian noise, but if your noise isn't Gaussian, then that might actually not be a good model. We can talk about that later, actually. But imagine I'm trying to model any other thing, like height as a function of age. Okay, not something where you have thermal noise. Then you certainly wouldn't want Gaussian noise. Okay. So, and then the question is, how should you fit A and B? And we're going to talk about that now. All right. So this is just a description of the model again. And we're going to make further assumptions, which we need to state clearly. We're going to say the noise is going to be Gaussian with mean 0 and variance sigma squared. Okay? And then we're also going to assume that the data was independently and identically distributed from this model. Okay? That our observations are not necessarily correlated over time, if we're observing these things over time, and that they all come from this model. They don't come from different linear regressions, right? They're all coming from the same linear regression. All of these are assumptions, and if you make all of these assumptions, then we can actually solve the problem. That's enough assumptions to solve the problem. So we're going to say y is going to be a vector, y1 through yn, and x is a vector of the x's, and we can write down what is the probability of the observed outputs y, given the inputs x and the parameters theta. The parameters theta are going to be a, b, and sigma squared. Those are the parameters of my model. Okay? And that is written like this. The probability of y given x and theta, because of the fact that I assume independence, I can write that as the probability over all the data points n, the probability of each data point. And because I assumed that they were identically distributed, I put the same kind of expression here for every data point, except I'm replacing it with the xn, yn pair. So independent, identically distributed allows me to write this. This term is known as the likelihood. This is the likelihood function for the parameters theta. And now, because I assumed Gaussian noise with 0 mean and variance sigma squared, I can substitute this term here for a univariate Gaussian density, which has the following form. This says that y is Gaussian with mean ax plus b. So remember, epsilon n was 0 mean, so therefore y has mean ax plus b. Okay, that's how come we can write this expression here. So now we're done, basically. We've written down the likelihood. But if, by thinking about this procedure, you can come up with any other noise, any other structure to it, and other assumptions, and then you would have to rewrite the likelihood for that. Usually, once you write down the likelihood function, the rest of your life is much easier, because you've sort of now turned your word problem into a bit of mathematics that needs to be solved. Okay, so that's our likelihood function. And now we're going to solve this using the maximum likelihood method. The maximum likelihood method says, take our likelihood function and find the parameters theta that maximize the likelihood. Okay? So this is a way of finding a point estimate for the parameters, a single value of the parameters. So we're going to find the thetas that are the maximum of the likelihood. Argmax means find the theta that maximizes this function. Arg stands for argument, right? Which is equivalent to argmax of the log likelihood. Okay? Because logarithm is a monotonic function, so the location of the maximum is the same even if I apply a monotonically increasing function. Okay? The log is very useful because it turns my product into a sum, and then life becomes easy when I have a sum. It's also numerically a good idea to do. So I'm going to argmax the likelihood function, log likelihood function, which I'm going to call L of theta. And now I'm going to do a couple of tricks. One of them is I'm going to, remember, my model said y equals ax plus b. So I had two parameters, a and b. I'm going to concatenate my two parameters into a vector beta. So it's a 2 by 1 vector, AB. And then similarly, instead of dealing with x, I'm going to concatenate x into a 2 by 1 vector with a 1 at the bottom. So beta transpose x tilde equals ax plus b. Okay, this is just a little bit of linear algebra, so that what I can write is that my model says that y has a mean beta transpose x tilde. Okay, so going back to the previous slide, here, instead of y minus ax minus b, I'm going to have y minus beta transpose x tilde. It's just a change of notation. But let's look at what else is happening here. My log likelihood is, because I took the log, the product on this side turns into a sum over data points n of the log probability of a Gaussian. And a Gaussian, if I go back to my previous slide again, a Gaussian has this form. When I take there's a constant, which I'm not going to worry about right now, and then the log and the exponent cancel, and so I get this quadratic term coming out. Okay, so what I get is a quadratic term, something squared, summed over the data, minus that constant term. And there's n versions of that constant term, so we get n over 2 log of 2 pi sigma squared from the Gaussian constant. Okay, so now I can take this quadratic term, I can expand it out. That's what's in this square brackets. I expand out the quadratic and I bring the sum in, and I get this expression. I can move the sum around a little bit. So a little bit of linear algebra in here. If I was doing this one regression lecture in an hour, I would do that on the whiteboard for you, but I won't, so that we can get through other things. But you can do this at home if you want, or at your desk. Okay? So we just write out this expression. It looks like this. That's the log likelihood. And how are we going to maximize this? We're going to maximize this by taking the derivatives of the log likelihood with respect to our parameters and setting them to 0. Okay? Yeah?
I have a question. In this case, vectors are a column vector, aren't they?
Yes.
So that term should be swapped. Not the last one. This one.
This is...
No, not the last one.
Sorry, this is...
Yeah, this one.
This is a row times a matrix times a column,
okay.
which ends up being a scalar. So in the end, what we have is the log likelihood is a scalar function, and there's a scalar here, a scalar here, and a scalar here. This scalar is quadratic in beta, this is linear in beta, and that doesn't include beta. But beta is a vector. So then we can take derivatives of the log likelihood with respect to beta, that vector, and this is where you combine some ideas from linear algebra with some ideas from basic calculus, and you get this expression out. It's this general case of the special case, which is how to take derivatives of a quadratic function with respect to something. So you get this term popping out, and you get this term turning into a linear term, and then the 2 cancels that 2, and this term, because it's a quadratic, appears twice, so that 2 cancels that 2 as well. So this is the derivative of the log likelihood with respect to beta, and then we set that derivative equal to 0, and what we get is something very famous, which is called the normal equations. And the normal equations, I've written them out naively for you. It's the solution to a linear system of equations. It's essentially, this is a, how big is this matrix?
It's d times d.
2 by 2 in this case, because it's a, yeah, your d plus 1 times d plus 1 in the general case, but in this case it's 2 by 2, because x tilde is a 2 by 1 vector. So this is a 2 by 2 matrix, you invert it, and then you multiply it by a 2 by 1 vector, and you get beta hat, which is a solution to maximum likelihood. And then if I want to take, if I want to figure out my noise variance, I take the derivative of the log likelihood with respect to sigma. I get an expression like this. This thing in blue is just this thing, okay, with beta hat plugged in. And then what I get is sigma squared is the sum of these blue residual terms squared divided by n. So it's the average of the residuals of my line. Okay. So that's it. That's how you solve linear regression in 2 slides. And now we're going to use this. Okay. So let's generalize this before we take a break. So we used a couple of properties to do this derivation. And here are some useful rules for derivatives with respect to vectors. The derivative of A transpose X, that's a scalar with respect to X, we're going to say is A transpose. There's a convention here. You could say it's A or A transpose. We're just going to say it's A transpose. And that's the convention I think most people follow. Okay? That's a dot product, and this is just the generalization of the derivative of AX with respect to X is A. Okay? Slightly more interesting, we can use the above and the product rule to show that the derivative of this quadratic form with respect to X looks like this. That's the product rule of calculus. We're going to take this product and divide it into 2 different ways, and we get this expression. If A is symmetric, then we would get this, basically. Okay? And then this is slightly more tricky, but we'll occasionally need to use derivatives of the log of the determinant of a matrix with respect to the matrix, and that's A to the minus inverse transpose. And that's just the generalization of the derivative of the log A with respect to A is 1 over A. Well, derivative of the log of a determinant of a matrix is the inverse of the matrix transpose. Okay? I'm not going to prove that, but that's just useful. Okay. Now let's make this more interesting. So 1D linear regression is not all that useful. But what about if you have X living in higher dimensions, in D dimensions? Well, now your model might look like this. We have coefficients beta 0, which is applied to the constant, beta 1 through beta d applied to the d dimensions of X, and then some Gaussian noise epsilon. And fortunately, we can write this in exactly the same form as we had before, as beta transpose X tilde, except that beta is now this vector, this d plus 1 dimensional vector beta 0 to beta d, and X tilde is a vector that consists of a 1, I now put it at the beginning instead of at the end, a 1, and then followed by the vector X. So again, it's a d plus 1 dimensional vector. So the good news is, by solving one-dimensional linear regression, we already have solved what to do in the multi-dimensional case, in the vector-valued inputs case. It's again just the normal equations. To remind you, the normal equations involve solving a linear system. Here it's this is now a d plus 1 by d plus 1 matrix. This is a d plus 1 by 1 vector. And that's a d plus 1 by 1 vector. And the noise variance is just, as before, the sum of the squared residuals, where I plugged in b hat, beta hat, divided by n. That follows from the same derivation as before. Okay, again, very basic, but useful to do it. But what about nonlinear regression? So these nice pictures I had with the polynomials, well, how do we do that? Well, we solve that as well. Because all we have to do is we write our model, our mth order polynomial like this. Now, beta is an m plus 1 dimensional vector. All right? X is the vector that, sorry, x tilde is the vector that has 1, x, x squared up to x to the m. It's a vector that looks like that. So now, again, we have it in exactly the same form as this. And therefore, we know that the maximum likelihood solution for the polynomials case is exactly this as well. Okay? So we can do polynomial regression. That's how I got these curves. Okay? Let's do one more. Now, what about what's called basis function or nonlinear regression? So what's special about the polynomials? There's nothing special. I can use any functions I want of the data. So instead of using polynomial bases, we can use all kinds of other bases. You know, Gaussian bumps, sinusoids. Think of it as sort of, regression in sort of Fourier space, wavelets, splines, etc. So now our general model, these models tend to be called basis function models, is that y is the sum of some coefficients beta k, some basis functions, these are fixed basis functions, phi sub k, applied to our original data, plus some Gaussian noise. And, a nice example of this is the radial basis function, which was interesting historically. It was very popular around the same time as neural networks were popular in the 80s and 90s. And this sort of basis function regression is the key component of a layer of a neural network as well these days. Okay? So, well, again, we've solved this already. We just need to define our x tilde to be phi of x, which is phi 1 through phi big K of x. So now x is d-dimensional, but we've mapped it into k dimensions. And d could be smaller or larger than k. All right? And our betas are solved with the normal equations. So I'm sure most of you know what a support vector machine is, or some of you have heard of a support vector machine. This idea of taking your data and mapping it through basis functions is an example of the kernel trick. Okay? The kernel trick just maps your original data into some feature space, phi, and then applies a linear method in that feature space. So this shows you how to do least squares kernel regression. Okay, and it was well known, a long time ago. Any questions about that? Okay. All right. Now let's question our assumptions a little bit. So we assume Gaussian noise, but imagine our data look like this. Okay, look at this data. What can you tell me about this data?
There are a few outliers.
Yeah, there are a few outliers. And actually, if I assume Gaussian noise, but my noise is not Gaussian, then this point here is going to pull down my regression line massively. I might get a regression line that looks like this. That's the regression line that minimizes the squared error. It's also the regression line that maximizes the likelihood under Gaussian noise. And it's because my noise assumption was wrong for this data. So if we want to be robust to outliers, then maybe instead of Gaussian noise, we should use what's called heavy-tailed noise. Heavy-tailed noise allows discrepancies that are large. It essentially ignores, to some extent, the effect of those discrepancies. All right? So here is the likelihood for Gaussian noise. here is a different likelihood for Laplacian noise. And Laplacian noise looks like this. It might have the same linear form, but the distribution, instead of depending on the square distance from the line, it depends on the absolute distance from the line. So it's less sensitive to these outliers because if you think about it, these outliers act like a spring on the line and pull the line down massively. It's a big force, but if that spring is somewhat, aphysical in that its energy only grows linearly instead of quadratically with the stretch of the spring, then you would imagine this data point would have less effect. And you can plug in any likelihood function you want and solve for linear regression, except that your solution might not come out as nice as these normal equations, which you can solve analytically. But you can solve for these things numerically instead. Any questions about that?
One question?
Yeah.
How do you define a heavy tail again?
Okay, heavy tail formally is defined in terms of the kurtosis of a distribution. Okay, so you have the different moments, the mean, essentially variance is centralized, second moment, then the third moment gives you the skew, which tells you whether it's skewed one way or the other. The fourth moment generally is what captures the heaviness of the tail. So it's a convention, but people say anything that has more kurtosis or excess kurtosis above the Gaussian is considered to be heavy-tailed. Okay, these are just words, right? But in practice, what it means is you put more mass in your tails and therefore less mass around the center. All right. So this is how to deal with outliers, or one little way to deal with outliers. And now I described doing maximum likelihood. I want to introduce some further notation and terminology. So the key driver of learning is almost always, in almost every model in machine learning and statistics, the likelihood function. You've got to really feel comfortable with likelihood functions. And what you do with the likelihood function depends on whether, what kind of philosophy you have, in a sense. So in Bayesian learning, which is a lot of what my own research is about, we treat the likelihood function as just part of the whole modeling framework. And essentially what we say is, there is no rule of probability theory that says you should maximize the likelihood. The maximum of the likelihood might be a good thing, but for when you have lots of data, it is provably a good thing. But when you don't have a lot of data, or when your model is complicated, there are lots of problems with just maximizing the likelihood. So is there a, say, more sound theoretical framework for what to do when you're learning from data? And the basic framework is apply the basic rules of probability. Okay? And so that says you have some data, call them y1 through yn. In this case, you might have some models, m, m prime, etc. These could be your different polynomials. These models might have some parameters, theta. And then what Bayesian learning says is essentially, there are two kinds of things in the world. There are the things that you've measured and the things you haven't measured. The things you've measured are called the data. The things you haven't measured, well, you haven't measured them, so they're unknown. Okay? And if they're unknown, the only coherent way of dealing with unknown stuff in the Bayesian world is through probability distributions. Okay? So probability distributions are going to be our language of representing our uncertainty. It doesn't mean we believe they're random. Okay? I hate the word random. Random suggests that, let's say I close my eyes and I say, well, I don't know exactly how many people there are in this room. Okay? It's not that there are a random number of people in this room, okay? I could count them, but I haven't counted them, and my visual system is not good at counting number of heads in a room. I'm uncertain about how many people there are, so I'm going to say they're between 15 and 25 people, and I'm going to represent my uncertainty with a probability distribution, okay? Now I can start counting, and that's collecting data, and I can update my probability distribution as I collect data, and my uncertainty shrinks until I've learned something. As I count, I'm going to learn something about how many people there are in the room. So the Bayesian framework says, well, our models are uncertain, so let's put a distribution capturing our uncertainty about what's a good model. Our parameters are certainly uncertain, so we could put a distribution capturing our uncertainty in the parameters, and then we can measure the likelihood function, which is the probability of the data given the parameters and model assumption. The basic rules of probability tells us that if we want to learn about the parameters given the data and the model assumption, we should apply Bayes' rule that follows from the sum rule and the product rule. And what that tells us is multiply the prior uncertainty with the information given by the likelihood, renormalize, and then you get a posterior distribution which captures your new state of knowledge. And there's no real difference between a prior and a posterior. It's just your state of knowledge before and observing that particular bit of data. Your posterior over the parameters is the new prior you should use if you collect more data. Okay? That's the basic Bayesian framework, and you can apply this at the level of models as well. So again, some terminology. Maximum likelihood corresponds to taking the argmax of the likelihood function, which we've just shown for linear regression. Maximum a posteriori uses a prior, but it's not a Bayesian framework. In my mind, it's sort of a poor cousin of maximum likelihood and the full Bayesian framework. It says use a prior, but then maximize the posterior density, which is this quantity here. So what is that? That maximum of the posterior density is the same as maximizing, if you take a logarithm, it's the same as maximizing the log likelihood, just like that, plus the log prior. Okay? That's map, maxima posteriori. Then there is regularized maximum likelihood, or just regularization, where what you say is that you have some data, you define a loss function that measures the loss between the data and a particular setting of the parameters. Okay? And that's a loss function over your training data. Now, many loss functions are equivalent to log likelihoods. Not all, okay? But most that are commonly used are simply the logarithm of some probability distribution over the data. Okay, so that's the loss here. And instead of minimizing the loss directly, you minimize the loss plus some regularization parameter, lambda, something greater than 0, a function r of theta, which is called the regularizer, which you use this term here so that when you minimize this loss, you avoid overfitting, okay, overfitting to the training data. All right? This is regularized, it's related to empirical risk minimization or regularized maximum likelihood, or penalized maximum likelihood is sometimes called. It's very similar in form to doing map. There's a subtle difference in that in map you're assuming this is a density. So map is not invariant to transformations of the parameters, whereas regularized maximum likelihood or empirical risk minimization is invariant to transformations of the parameters. So there is a subtle difference between the two, but most people equate map with regularized maximum likelihood. Okay? And then there's Bayesian learning, which says don't minimize or maximize anything, just compute Bayes' rule as best you can. Any questions about this?
Model is your likelihood function?
Yeah, the model M actually should capture, the model should be a representation of all of your assumptions. So people often make this funny distinction where they assume that the likelihood function is given to them, and the prior is something that's totally arbitrary. And actually, the likelihood function is not, in most real applications, the likelihood function is also an assumption. So everything is assumptions, really. The only thing that's not an assumption is the data from the sort of, Bayesian perspective. Okay, I'm not going to talk much about learning theory. Learning theory is in lecture 6, or it's actually not even in lecture 6, where we analyze the behavior of these types of algorithms and methods as we get more and more data. Yeah? Okay, we're going to talk about classification. Classification is really the bread and butter of machine learning. Most applications of machine learning that people kind of think about are often, classification problems. And I already went through the example of this, the basic idea of classification with C classes, and this example of the iris data set. And you can look at this picture and think about various things, like, for example, what can you tell me about this picture? What can you tell me about the different classes? Anything interesting?
What's the question again?
Can you tell me anything interesting about this data from looking at the picture?
It's one class is linearly separable, the others.
Yeah, the red class seems to be linearly separable from the other ones. That means you could draw a line that's not quite a line because it's different. But you could draw a line separating that.
Yeah, but this is just one projection.
This is just one projection, and the data lives in 4 dimensions. So it might be that the blue and the green are also linearly separable if we projected it in a different direction. So it's quite hard to tell. I would also say that Mr. Anderson might have been tired when he labeled this one. Like, I don't know for sure, but this one seems kind of far away from these guys. Maybe this one was actually a member of this class. Could be an outlier in terms of classification and so on. And the data's been discretized and all sorts of other things. Okay, so this is a classification example. Let's look at the problem again. I'm going to try to maintain fairly consistent notation. So our data set is D, it's pairs of X's and Y's. And again, we're going to use X tilde to be X followed by a 1, because we're going to need that sort of extra intercept term to build our classifier. And in this case, we're going to simplify things and think about just binary classification. So our labels are just going to be 0 and 1. At the end of the lecture, we'll look at how to generalize that to multiple classes. So here is a simple model of linear classification. It just says, take my X tilde vector, multiply it by a vector of parameters beta. Okay, take a dot product, in other words. If that dot product is greater than or equal to 0, say it's class 1. If it's less than 0, say it's class 0. So that's what's called the Heaviside function, also known as the threshold function or step function. Okay, so that would be a deterministic classifier. And again, for the same reason that I wasn't happy with the linear regression model when you didn't assume any noise, I'm not going to be happy with this as a model. Okay, this is not really a good model because it doesn't allow for any errors. It doesn't allow for any noise or mislabelings or anything like that. It's a deterministic model. So how do we make this smoother, not so deterministic? Any ideas?
Swap the h function to sigmoid.
Yeah, we change the h for a sigmoid. And then the output we have to interpret differently. It's not just y, it's going to be the probability of y taking on value 1. So let's do that. In fact, same setup as before. We're going to replace the Heaviside function with a sigmoid function. Sigmoid just refers to the shape of a function. It's like an S. And a common sigmoid function is what's called the logistic function, 1 over 1 plus e to the minus z. And that logistic function is plotted here, okay? It's a smooth version of the Heaviside step function. And then the output of that we're going to interpret as the probability that yn takes on label 1. So obviously, the probability that it takes on label 0 is 1 minus that. Okay? And sigma could be any monotonically increasing function that maps into the 0, 1 interval. The logistic function is a common choice. Now, this model is often called logistic regression because it looks a lot like linear regression, that we just did in the last lecture, except that instead of Gaussian noise, it's assuming that the noise is some nonlinear mapping and then turning into a noisy coin toss. Okay? That's often called logistic regression. It's a simple model, it's a linear model, and that's why we're going to start there with our whole understanding of classification methods. Okay, so I'm going to call it logistic classification, although the rest of the world calls it logistic regression, because I like to sort of just distinguish between regression methods that map onto reals and classification methods that map onto discrete class labels. This should really be called logistic classification in this terminology. Okay, so what does logistic classification look like? Well, I've told you what the probability that y equals 1 is. It's this sigmoid applied to the linear function of x tilde. And the probability of y is 0 is 1 minus that, which for the sigmoid logistic function, this function is anti-symmetric, which means that if I do minus z, I get 1 minus the function. It just happens to be that way. And so 1 minus sigma, here, note that 1 minus sigma of z is sigma of minus z. So I can write it as logistic of minus beta transpose x tilde. Okay? Now we're almost done, actually, because we've written down what the probability of a single data point is. And now if we think about this model, it defines a Bernoulli distribution, sort of like a coin toss distribution, over y, the label variable, at each point x in the real space. Okay? A lot of these little coin tosses at each point. And remember that the Bernoulli distribution looks like this. Theta to the y, 1 minus theta to the 1 minus y. And in this case, theta is going to be the output of my logistic function. Okay? So when I say we're almost done, what I mean is that we can almost, in fact, right here, we can write down the likelihood for our parameters beta. Okay, the likelihood function is going to be the probability of all of the labels given all of the x's and beta. If we assume independent and identically distributed data under this model, just like we did before, then that's the product over data points of the probability of each data point. And the probability of each data point is given by sigma of the linear function to the y times 1 minus sigma of the linear function to the 1 minus y. And this is just some function of beta which we can optimize. Now let me tell you a little bit about, these exponents, they get some people confused. If you've seen them and you're familiar, then it's fine. Y is a binary variable. It takes on only two values, 0 and 1. And a really fun thing is that when we write, if we want to write an if statement in mathematics, we can use taking to the power of a binary variable. Okay? If y equals 1, then we get this, right? If y equals 0, this term cancels out and we get this. Okay? So every time you see a likelihood function that has if condition then blah, if condition then blah, you can write it by coming up with an indicator variable and then taking a product of terms in those indicator variables. Okay? That's our likelihood function. And now, just like for linear regression, we can consider maximizing this as a function of beta. All right, so that's equivalent to maximizing the log likelihood, which is the log of the probability of all of the data, which is the sum over the data points of the log likelihood contribution from each data point. And so we have a sum over n of y log sigma plus 1 minus y log sigma of minus the argument. Okay, that's the same thing as here. If we just take the logarithm of this whole expression, we get y log sigma of the linear function, 1 minus y log 1 minus sigma, which is the same as sigma of minus the argument. Okay, so that's just a little bit of algebra. And now I can take derivatives of this thing using the fact that for the logistic function, derivative of log of the logistic function with respect to z is just the logistic function applied to minus z. Simple fact to show just using basic kind of A-level maths or something, high school mathematics. Okay? And we're going to define this Zn, just because the notation is just going to get unwieldy, I'm just going to define Zn to be the dot product of the parameters beta and my data point x tilde, okay, for the nth data point. So now, the derivative of the log likelihood with respect to beta is the sum over data points of yn times sigma of minus z times x tilde. This is just by applying a little bit of calculus to this. Minus 1 minus yn sigma of zn x tilde. I'm going to rearrange some terms, and then this is going to be the final derivative of the log likelihood with respect to beta. It's the sum over data points, like we had for linear regression, of terms that look like this. And what we would really like to do is solve for beta. Okay? So where is beta in this equation? Sorry?
Z.
Sorry?
Z.
Yeah, beta is sitting inside of z, okay? Beta is in here. And it would be really nice to solve for beta analytically, but there is this nonlinearity here. So if I set this equal to 0, then I get n nonlinear equations to solve for beta. So I can't do this, unlike linear regression, I can't do this analytically, which is annoying. But there's some nice intuition about this log likelihood, which maybe you can see when I do. I'm going to do a little bit of a MATLAB demo, and you might see that intuition coming in. But what the log likelihood tells you is for every data point, there is a contribution. And what is y? Y can take on only the values 0 and 1, okay? And what is sigma? Sigma is the predicted probability of y. So think about the case where sigma is very high, okay? It's like 0.99, all right? If y is 1 and sigma is 0.99, then there isn't much error. You predicted that data point n was going to be in class 1, and it ends up being in class 1. So the derivative of the log likelihood has a very small contribution if your predictions are good. Similarly, if sigma is 0.01 and your class label is 0, then this term is going to be tiny, 0.01, right? It's always multiplied by the direction, the location of the x. Let's forget about that for now. The error is given by this. When the error is small, the contribution to the derivative is small. When you make a whopping mistake, like you predict 0.99, let's say you predict, 0.9, then Hillary Clinton is going to win, and then Trump wins, you've made a whopping mistake, and you need to change your model drastically. So when the error is large, the model will change more drastically. When the error is small, the model will change very little. That's a nice thing about all of these optimization methods and gradient methods. They actually, if you stare at them enough, there's a lot of intuition behind what's going on. Okay, And this is a scalar. This tells you a positive or negative number by which you're going to change things. This is a vector. That's going to tell me what direction I should change it in. What direction should I change the vector beta in to align itself with the data point x tilde? And all of these forces, they will balance out to the point that's the maximum likelihood point, which is giving you the most happy model given the data as measured by the likelihood. Okay, so in practice, we can't solve for this analytically. So what we do is we apply an iterative algorithm to solve it for it. And this is like going to be, again, you will have gotten or will get lectures on optimization, but it's necessary for me to talk about this to explain what's going on. This is the simplest kind of optimization, numerical optimization method you could imagine. I have a log likelihood. I want to maximize that. So I'm going to take the derivative of the log likelihood. I'm going to start my parameters beta at some initial conditions, and I'm going to do hill climbing. Okay, I'm going to actually move over iterations of my algorithm. I'm going to move my beta. So beta at iteration t plus 1 is going to be beta at iteration t plus some learning rate eta times the derivative of the log likelihood. Mountain climbing, whereas you stand on the mountain, you measure the slope of the mountain, and you take a step eta in the direction of the slope. That is guaranteed you, if you use small enough step sizes and so on, it's guaranteed you to end up at some local optimum of the mountain. Okay? And it turns out for a logistic classification that there is only a single global optimum generally. But in general, if you apply this to a more complicated model like a neural network, you'll end up at a local optimum of the likelihood. Okay, so now this gives us this equation by just plugging in the log likelihood. And this is what's called, again, a bit of terminology. This is called a batch learning algorithm because, it essentially has to consider the entire data set. All n data points have to be considered before you take one step. Okay? And in the old days, when we had, lots of time and small data sets, that was fine. But if we have a huge data set, this seems kind of crazy because we're going to have to look at all of the data before we take one step in parameter space. The extreme other version of that is the fully online learning algorithm, which says just consider a single data point at a time. All right, and now what I've done is I've replaced the index n, which goes with the data points, with an index t. So every iteration of the algorithm, t, I'm going to consider a single data point, a single pair, x tilde y, and I'm going to take a little step eta in the gradient direction of that one data point. Okay, that's what's called online learning. And in practice, people do things that are in between, like mini batch learning. Mini batch learning will consider a small number of data points, compute the gradient over the small number, and take one step after that. Okay, any questions about that? Okay, and in fact, actually, although this is called steepest gradient ascent or steepest descent if you're going down the negative log likelihood instead of up the log likelihood, you could use any standard optimizer. We have a cost function, right? We can compute the derivatives of that cost function. So we could plug them into conjugate gradient optimizers or Newton's method or any kind of optimization package out there. But this is quite useful to look at because it's a very standard optimizer that will be useful when you try to think about what neural networks do, for example. Okay, so here's a demo of online logistic classification. And I'm going to run that demo for you, hopefully. And warning, I'm going to run a demo in case it's important. And all right, so let's see how big I can make this. Okay, can everybody see that okay? So here is the origin, 0, 0. The purple line here is going to be beta, okay? And beta, this is at the initial conditions. Beta is pointing in some random direction, and white means class 1, and black means class 0, okay? And the reds are in, sorry, maybe bad color notation. The reds are going to be in class 1, and the blues are going to be in class 0, okay? So I'm going to apply online gradient ascent to this logistic classification model. And I'm going to do it one step at a time. And I want you to watch the data points as they come in and what's happening to the vector beta. Okay. So data point comes in over here, big error, right? So this guy moved. Another error here, misclassified. This is going to move. It's moving. Okay, this one is sort of correctly classified. This one is still misclassified, etc. The shades represent contour lines of probability. So this is very high probability of class 1, very high probability of class 0. Okay? So I keep running the algorithm. Okay. The vector is getting longer. The vector getting longer represents the classifier getting more confident. So the uncertainty area is shrinking as the vector is getting longer. Okay? And at some point, this looking at one data point at a time. And now I'm just showing you all the data it's seen during learning. So this is the last step. You can see that it started pointing in the wrong direction, and after some learning, it's now pointing in the right direction. And we can even count. This is the origin, so that's the probability 0.5 boundary. How many errors is it making?
1.
It only makes one error eventually on the training data. Okay? Any questions about the demo? The demo is just amazingly simple in terms of the code available for the demo. You can actually find this online it's MATLAB code. It's called lrdemo.m, and it's on one of my web pages. It's amazingly simple because the meat of the learning algorithm is one line of code. And the rest is just plotting and looping over that one line of code. Okay? If I plug in a different derivative, I'll get a different online gradient ascent algorithm. Okay, that's logistic classification. Let's make it more interesting. Like before, we start with simple, and then we add complexity, and we try to make it more and more interesting. Okay, so let's talk about something that can happen. Let's talk about something that's a little bit funny that can happen. So consider this example, okay? And now, what if these two classes are perfectly separable by a line, okay? So the line, actually the line that separates them is the line that's perpendicular to that purple line, just to be clear, okay? That's the decision boundary. If these two classes are perfectly separable, then what's going to happen to this algorithm as it sees more and more data? Any ideas? Sorry, who said that? Yep. The weights, the beta vector goes to, the norm of the beta vector goes to infinity. Okay? This is, in fact, I can demo it very nicely because this will just keep growing and growing and growing in that direction. All right? I think I'm further breaking this guy. You might have to buy another one after I'm done with it. Okay, so, and why is that? Why does the vector get longer and longer? Yeah?
Because the two classes are separable and the classifier gets insanely confident.
Yeah, the classifier gets, I like the use of the word insanely. It gets insanely confident because it's trying to maximize the likelihood. If you have all of the training data on the correct side, the best way to maximize the likelihood is to push all of the probabilities towards 0 and 1, And the best way to do that is to make the norm, the length of this vector, longer and longer, because then the dot products will become either very large and positive or very large and negative. When you pass them through the sigmoid, they'll go to 0 and 1. So maximum likelihood has that interesting property, which really is a bit of overfitting, right? You're getting overconfident. Okay, and so if we kind of take our terminology that we learned in the previous lecture, and we say, okay, let's do maximum a posteriori. Let's put a Gaussian prior on beta with some variance lambda. Well, what does that correspond to? If we take the log of that Gaussian prior, then what we get is a term that is quadratic in beta. It's actually the norm of beta penalizes the length of beta squared with some penalty term at the beginning. And now if we do map, instead of maximizing the likelihood, we maximize the penalized likelihood with this regularizer added on. Then what happens? Well, in the perfectly separable case, although the likelihood prefers betas to be, infinitely long in the direction of the correct class boundaries, this prior term or this regularizer is penalizing the length of the vector. Okay, it's shrinking it down. Oh my goodness, this is really not going well. Not designed for actual use in a lecture. All right, so balancing the likelihood and the regularizer, you will get some vector that is not overconfident. Okay? Now, what about Bayesian learning? What would be the difference in doing Bayesian learning in this classification model? Any ideas? I mean, not just like you apply Bayes' rule. Any answers that are better than, okay, you just apply Bayes' rule? No. Okay, so what's actually, what the Bayesian approach tells us to do in this setting, and I'm going to use the whiteboard. What the Bayesian approach tells us to do is, I have a data set. It might look like this. Okay. Now, this is a class boundary that divides the data, right? This class boundary corresponding to a beta vector that's pointing in the orthogonal direction, that divides the data, right? But imagine what I had is a prior that just said boundaries could occur in any direction, a priori, all right? And then I observe data that looks like this. So imagine what happens there is that I take all of the boundaries that I considered before and I throw away, essentially, all the ones that don't divide the data. Okay? Now, what am I left with? I'm left with still a lot of uncertainty. Okay? So, my prior could be uniform, let's say, over all directions. My posterior over beta, given the data, is going to look like a probability distribution that puts probability mass on all of these different hypotheses, all of these different boundaries. Okay, so in fact, my final 50% class boundary will probably look the same as before, but I will get some nice uncertainty contour lines that tell me, other possible boundaries that might be consistent with the data. Does that make sense? So the idea behind Bayesian learning isn't just blindly applying Bayes' rule, it's considering all the uncertainty that you might still have after having observed the data. And we've only observed 1, 2, 3, 4, 8 data points. So we're going to have a lot of uncertainty. If we observe 8,000 data points, our uncertainty will shrink eventually to the maximum likelihood solution. Okay? All right. So, what about nonlinear classification? We did this trick with linear regression. Let's do it with classification. So here is the simple way of doing it. I'm going to just map my data through some nonlinear transformation. Like, for example, my x1 and x2 coordinates, I'm going to map them into x1, x2, x1 times x2, x1 squared, and x2 squared. So I'm mapping from 2 dimensions to 5 dimensions. And what kinds of decision boundaries can I get by linearly combining these 5 different dimensions? Anybody remember the name for that from high school? Not lines. Not hyperplanes, because there's in this space you can get parabolas, hyperbolas, conic sections, yeah. So the set of all conic sections is what actually you're representing by mapping from these 2 to these 5 dimensions. Okay? And let's demo that. Again, I'm just going to apply exactly the same learning rules before. I've just transformed my data from this space to that space. And I'm going to do another MATLAB demo. Okay, so now I can't draw, the contour plots are the interesting part because all I'm doing with the vector is I'm drawing the first 2 elements of that 5-dimensional beta vector, okay? It's still quite useful, but, all right, so let's just see. Again, the same kind of demo, data points come in. Ooh, decision boundaries are nice and curvy. You can jump around. Same code, basically. That one line in the middle is different. You see some nice conic sections, right? Parabolas, all sorts of fun things. Okay. So that's all the data it's seen. And now, if you look at the shaded area, the 50% decision boundary is that one, and it's perfectly classified all the reds from the blues. Okay? Same learning algorithm, same everything, just mapping into a higher dimensional space. Okay, go back to the lecture. Nonlinear logistic classification. And then, what about if you have more than 2 classes? Well, if you have more than 2 classes, we can call this multinomial classification or discrete categorical classification or something like that, or softmax classification. So what do we do if we have multiple classes, like 1 through C? Then instead of using the logistic function, we can use the softmax function, which now is going to have a different vector beta for every class. Okay, so I have, let's say 10 classes. I'm doing digit classification. So I'm going to have 10 different beta vectors. And my probability of y belonging to class C, given x, is going to be e to the beta sub c dot product with x divided by the sum over by 10 classes of e to the beta sub c prime dot product with x. Okay, so obviously we divide by the sum over classes here because these probabilities should sum to 1 when we sum over all the classes. And this particular softmax function has a lot of very nice properties, you know, just like the logistic function. In fact, it is a generalization of the logistic function. Okay? All right, so here are some exercises. If you're keen to do them afterwards at some point, just show that the softmax function is equivalent to doing logistic classification when c equals 2. Implement online logistic classification in your favorite language. I mean, I used to program in MATLAB, but you know, use whatever you want. Implement the nonlinear extension. Investigate what happens when the classes are well separated, what the role is, etc., etc. Okay. Good. So that's classification. How are we doing? Okay, let's see how we're doing on time. So we have an hour to go. I can talk about clustering. I can talk about the original plan would be clustering, dimensionality reduction, and then advanced, and then no time left for advanced material. That's the original plan. Okay. Are you happy with that plan? Yeah? I think it's good to go through the basics. I will, you know, I'm around, right? I'm a, you know, faculty fellow, right? I'm around and I can give my more advanced lecture at some other point in the future. So I think it's better if we stick to the plan, and you'll see the kind of schedule, the syllabus for the advanced lecture, and then you can get the sort of terminology in your head. You can ask me, I'd like you to talk about X and not Y or whatever. I mean, I can do customized lectures as well. All right. So, let's do clustering. Remember, that's what clustering was. Find points that are similar and put them in a group together. The best way to understand clustering is to start with a very classic algorithm. Again, I'm going through algorithms that are, you know, they're each at least 50 to 100 years old. Okay, that's where we need to start. And the algorithm we're going to start with is called the k-means algorithm. So here's how the k-means algorithm works. We have a data set D. It's got n data points, and they live in some d-dimensional space. Okay, sorry, calligraphic D, regular uppercase D. Okay, different symbols. So now I'm going to, the algorithm is stupidly named, but it's at least 50 years old, so we can't really change the name now. It's called k-means because I'm going to assume there are k clusters, okay? And each cluster has a center or mean, let's call it m sub k, which are points in this d-dimensional space. Here's how the algorithm is going to work. Instead of writing down likelihoods, this time around I'm just going to show you what the algorithm is. Then we'll think about the relationship to models and so on afterwards. So, repeat, for all the data points, find the nearest mean. Okay, initialize these somewhere. Okay, then for every data point, compute the distance between the data point and the means, and find the nearest center, nearest mean. And that data point is going to be assigned to that nearest center. Okay? Simple enough. I can substitute other distance measures here, but I'm just going to use Euclidean distance. Okay? So that's one step of the algorithm. Then the other step of the algorithm says, for all of the centers, recompute the location of the center to be the mean, that is the average in Euclidean space, of all of the data points such that the data points were assigned to that center. Okay? So now the means have moved around. So now we have to go back to this, reassign the data points to the nearest mean, and then go back to this, recompute the means, etc., until convergence. And it's not obvious this algorithm will converge, but I will prove to you later that it will converge. Okay? So until the assignments don't change anymore, when the assignments don't change anymore, then the means won't change anymore, and then the algorithm converges. All right?
How do you initialize centers?
Excellent question.
Arbitrary
Well, we can do that in the demo later. I'm going to explore that in the demo in a few minutes. But first I'm going to show you an example, a real-life demo. And this demo is thanks to Ian Murray, who's a lecturer in Edinburgh, who many years ago used to be my PhD student. And like as often happens, you know, I was away, I couldn't teach, so I asked Ian to teach the k-means algorithm to my students, and he went to the supermarket, he bought himself some lemons and oranges. So what did he do with these lemons and oranges? Well, he collected his own data for teaching purposes. He measured the height in centimeters and the width in centimeters of all of the lemons and oranges that he collected. Okay? And of course, we could do classification on this data. We could separate, we could build a machine learning algorithm that based on the heights and the widths is going to classify your fruit into lemons and oranges, and it would look like this, right? But instead, imagine what happens if you don't have these labels, lemons and oranges. And actually, you can see here that oranges seem to come in different sizes, right? So you can see some clusters in the data, and wouldn't it be wonderful if your algorithm could automatically discover the clusters in your fruit, right? So let's apply the k-means algorithm, as I've just defined to you here, to the lemons and oranges data. Okay, we're going to do that. We're going to have 1, 2, 3, 4, 5 clusters, okay, denoted by the big colored X's. The means are the big colored X's, and I want you to look at the initial assignment of data points to the different centers or means, okay? So the purple X has these data points assigned to it. These are closer to yellow than anything else. These are closer to black than anything else. Blue has this, and red has these data points. Okay? Because, you know, this is the closest thing to that is the red, right? So, on the first iteration of k-means, what's going to happen to the red mean, the red cluster? Where is it going to go? It's going to go down this way, right? Because the center of mass, literally the mean in Euclidean space, so the center of mass of these red points is somewhere around here. Okay, I'm going to guess it's here. Let's do what iteration of the algorithm? All right, I was close. I've seen this before, obviously. Okay, so the red in one iteration of the algorithm, there's no learning rate in this algorithm. It just jumps. This is a great algorithm. The red thing jumps here, the blue thing jumped there, the yellow thing jumped up, the purple thing didn't do anything. Okay? So now I reassign the data to the different clusters. So again, look at these red, these points used to be assigned red, but what's going to happen to them now? Okay? Obvious. Anybody paying attention? They're going to turn blue? Indeed. So I go back and forth. You can see that the points change color. And then the next iteration of the algorithm, pay attention to the red again. What's it going to do? Jump down to the center of mass of these data points. Are we done yet? Has it converged? What do you think? No, it still looks a bit funny here. Like these yellow points, they don't look quite right, do they? They need to change color. Yep. And then The yellow X moves. Are we still done? No. These blue points, these black points change to blue. Black jumps that way. Let's look here. These change to blue. Black jumps there. Are we done? Yes. More than less. Yes, we're done. The algorithm has converged. That was all, the entire algorithm, it converged in that number of steps. Okay? So the algorithm is very clear. It's been around for, I don't know, 60 years or so. And it's really widely used, like tens of thousands of papers, and almost every company that handles data runs k-means at some point to cluster their data. Right.
Do you use median or median?
In this case, I used mean. I can change my distance metric in many different ways. So one could do k-medians if one wants. Okay? Or other distance metrics that are, as long as it's a valid distance metric, you can apply this. Okay? Any other questions? All right, so that's clustering with k-means. It's just an algorithm. It seems a bit unsatisfying, right? Like, what's it actually doing? What assumptions does this algorithm make about the data? Can we understand the algorithm? I just talked about these probabilistic models and errors and noise and likelihoods. Is that related all to this algorithm? Do we know whether this algorithm converges or not? It looked like it converged on this case, but is it generally going to converge? All right, well, here's a really good way of understanding algorithms. If you have an algorithm that is an iterative algorithm, if it's actually optimizing something, if it's minimizing or maximizing something, that gives you a lot of understanding of what that algorithm is doing. Okay? So is there a cost function associated with k-means? And the answer is yes. Okay? So here is a cost function for k-means. So we're going to introduce we're going to change the notation a little bit because it helps us. I'm going to say there's binary variables s and k, which are either 0 or 1. And S and k equals 1 if data point n is assigned to cluster k. All right, that's going to tell me the colorings or assignments of my data points. And note that because every data point has to be assigned to one and only one cluster, the sum over the cluster, sum over k of S and k is 1. So there's only one in each row of this matrix, and all the other elements are 0. All right? That's the assignment variables. And now here is a cost function. This is a function of the s's and the means. And it's just going to be the sum of all the data points, the sum of all the clusters of s and k times the square distance between data point xn and mean k. That's the cost function. I didn't, how do I prove to you that that's the cost function? Well, the way to prove that is to show that every step of the k-means algorithm is trying to decrease this cost function. Okay? So here's a claim, which I'm not going to prove formally, but it's quite easy to prove formally. Okay? The k-means algorithm tries to minimize this cost function c with respect to these indicator variables and with respect to the means, subject to the constraint that the indicator variables are binary. And there's only, every data point is assigned to one cluster. So let's try to understand this. Let's remember what the k-means algorithm did. In the first step of the k-means algorithm, the first part of the algorithm, it assigned the data points to the means that were closest in Euclidean space. In this cost function, it factors over the data points. So if I'm data point n, and I want to minimize this cost function, then the only term I have to consider is the term that's snk summed over k of xn minus mk squared. If I want to minimize that, subject to the constraint that I have to choose one of the k's, the best way to minimize that is to choose the k for which my square distance to mean k is smallest, because these are all positive quantities, non-negative quantities, right? So I just choose that Snk equals 1 if xn is closest to mk, all right? So the first step of k-means is individually for every data point, minimizing this cost function with respect to the SNKs, holding the mk's fixed. And then the second part of the k-means algorithm, which changes the m's around, is minimizing the same cost function, except it's holding the assignments fixed. And for every k, it's choosing mk to be the center of mass of the x's assigned to it. Okay, so as a function of k, we only care about the data points that are assigned to mk because the weight of the other data points is 0, so they fall out of the cost function. And when we minimize the sum of square distances, the minimum of that is the center of mass. That is what the minimum ends up being. Okay? So to be clear, I'm not going to move the board because it's not that important. But what I mean by the center of mass is that mk is the sum over n such that Snk equals 1 of xn, these are vectors, divided by the number of data points. That's what the center of mass is, just the average of the x's. Okay. All right. So the k-means algorithm, every step of it decreases this, or it keeps it fixed. When it's fixed, then the algorithm has converged. This cost function is bounded below. The minimum, the smallest possible value this could have is 0, basically. Although, for most realistic problems, it will never achieve 0. So that guarantees that the algorithm will not go in loops and that it won't diverge or anything like that. And it turns out that in general, finding the global optimum of C is a hard problem. It's a computationally hard, NP hard, NP complete problem. I'm not sure which one. But in practice, the algorithm generally works quite well. Okay. Any questions about this cost function interpretation of k-means?
So basically what it means is that if that means in the worst case, every data point is enough.
Okay. When I've described the k-means algorithm, I've assumed k is fixed. All right? And so I have n data points, k is fixed, and in general, it's possible that the global optimum is very hard to find in that case. If the number of means equal the number of data points, then it would be very easy. The solution is put a mean on every data point, and your cost function is 0. If the number of means is 1, then it's also easy. Just it's the center of the data. But somewhere in between, we get computationally hard problems. Yes.
The interesting part is to figure out the process yourself. The K.
The K. Yes.
Yeah. Have a mean and upper bounds and fluctuate depending on the needs of the data set.
Right. So I think the other way of thinking about this question is, how do we know what K is?
Yeah.
Right? And the k-means algorithm doesn't tell you the answer. But,
It's an interesting problem.
this is an interesting problem.
After the talk.
Yeah, after the talk. There are about 100 papers trying to answer that question. How do we figure out K? Including, I've written about half a dozen myself. Okay?
That's nice.
And I have a nice answer to this, but it's going to be sort of predictable, my answer, from if you know anything about my research. Actually, I have 2 different contradictory papers with 2 different answers. Okay.
That's in the fixed data set scenario, the unbounded case.
Oh yeah, even in the fixed data set scenario, we can reason about what's a good number of clusters for the data, and it's equivalent to figuring out what's a good polynomial if I'm doing regression. It's equivalent in a very high level. It's a model selection question where we're trying to avoid both underfitting and overfitting. Okay, so that's the k-means cost function, and it's really nice to have a cost function. But to me, it's not quite enough, because cost function just tells me properties of the algorithm. Where does this cost function come from? Is this a reasonable cost function? Can we apply this cost function to all problems, or should we think about other cost functions? Okay, so let's think about that. And again, the link is going to be to probabilistic models. Okay, so a little bit of review. This is a multivariate Gaussian density, and you'll see in a minute why it's relevant. A multivariate Gaussian density is a density in d dimensions. It has a mean, call it mu, and a covariance matrix, call it sigma, and you can view this as fitting some sort of elliptical bump in d dimensions. Okay? So now I'm going to rewrite this multivariate Gaussian density. Instead of using the symbol mu, I'm going to use the symbol m sub k, all right, for obvious reasons in a minute. So that's going to be the mean, m sub k. And instead of a covariance matrix that could be any arbitrary kind of funny correlated ellipse, I'm going to use a spherical covariance matrix, an identity covariance matrix, so that these sigmas kind of disappear, all right? Then my Gaussian density is going to look like this. This is the squared norm. This term here is the squared norm of the distance between x and m sub k. It's appearing inside an exponent. And this is just a normalizing constant for a Gaussian density. Okay? How are we going to link this to k-means? Well, let's take a Gaussian, and what we're going to do is not just think of a single Gaussian, but think of k-Gaussians. K-Gaussian bumps, where essentially I'm going to model the distribution over data as a weighted mixture of k-Gaussians with different means. All right? So again, I might not remove the board a little bit so you can see. All right.
It's a mixture model, a weighted mixture of.
It's a mixture. It's called, this is what's called a mixture model in general. And in fact, it's going to be a mixture of Gaussians. Okay? And so a single Gaussian, I can represent it as having a mean and a covariance matrix, which I'm going to write down showing concentric ellipses. The density is going to fall off of this bump. I already said I'm not going to consider arbitrary covariance matrices, so I'm only going to be looking at circular covariance matrices, okay? Identity covariance matrix, and I'm going to have multiple of these Gaussians with different means, M1, M2, M3, and the same identity covariance matrix. Because I have 3 Gaussians, I need to put weights on them, so this density integrates to 1, and I'm going to put weights 1/3, 1/3, 1/3 in this example. Okay? That's a Gaussian mixture model. Any questions about that? All right, so now I have a Gaussian mixture model. I'm going to assume equal weights, equal mixing proportions. And here is the density for the Gaussian mixture model. I'm just repeating notation from the previous slide. And now imagine we observed which data points came from which Gaussians. In other words, imagine we knew these indicator variables, then the probability of the data and the indicator variables would be, for any one data point, it would be the product over the Gaussians of wk p of xn given mk to the power of snk. Weird, but remember what I said about if statements using math. snk is an indicator variable. So what this is saying is that the probability if snk equals 1, which it does when data point n is assigned to cluster k, then the probability of that configuration is the density of xn under mean k, right? Which is assigned to mean k, then it's the density under mean k. And then there's a term wk, which is accounting for the prior probability that Sn equals k, and that term is going to be 1/3 or 1 over k for everybody. So actually, it turns out that term is going to drop out. So then, for this probabilistic model, the likelihood function, assuming that the x's and the s's are both kind of observed, is the product over n of these expressions. Okay, that's just the probability of all the data under this mixture model, in this weird assumption where we're going to assume that the assignments are known. So that's the likelihood function. So I'm rewriting the likelihood function here from the previous slide, nothing new. And now we're going to set wk equal to 1 over big K. So this log, and we're going to take the log likelihood, so the log of this guy. The product turns into sum over n and k. Log of this expression, snk, comes down. Then we get log of wk, which is just log of 1 over k, plus log of a Gaussian density. Rearranging terms, we're going to get sum of nk, snk, log of a Gaussian density, minus n of these terms, log of 1 over k. So that's why you get a minus log k. So n log k, that's some weird constant that is not going to matter. Then this Gaussian, well, what's the Gaussian has, again, some constants, some normalizing constants here that don't depend on the data. They appear here. And then the action part, the log and the exponent cancel each other, and we get a quadratic term here. So this log likelihood is minus 1/2, this term in red, minus some constants. Okay? Now we've come to the final point here, which is maximizing this log likelihood with respect to both the means and the assignment variables is equivalent to minimizing the k-means cost function. And on purpose, I put that in red because this is the k-means cost function. And all the other stuff is multiplicative or additive constants. And the minus sign is why maximizing the log likelihood is equivalent to minimizing the k-means cost function. So k-means corresponds to a probabilistic model. It corresponds to a mixture model under the assumption that the clusters are equal size and the covariance matrices of the clusters are spherical and all equal to each other. Any questions about that?
What if we change these assumptions?
Wonderful question. So the reason I never use k-means is because once you realize that k-means is just a special case of a Gaussian mixture model with certain very restrictive assumptions, you start thinking, well, why do I need the clusters to be equal size? Can I make the cluster weights be a parameter that I learned from the data? And let's say one cluster has 10 times as many data points as another one. I don't want an algorithm that makes the wrong assumption there. What if the data is correlated? I don't want to have identity covariance matrices. I want my covariance matrices to adapt to the data as well. So essentially the generalization of k-means is basically fit a Gaussian mixture model to your data. And there's, entire chapters of books on that topic. Okay. Any other questions?
Does that mean that Euclidean distance falls out of this interpretation?
Exactly. It fell out the moment I said Gaussian densities with identity covariance matrix. Just like when I said Gaussian additive noise, the quadratic loss in least squares fell out. And if I have other, if I have outliers, k-means will do badly there because the outliers will capture a mean immediately, right? So again, we can, now that we've realized that this is a special case of a probabilistic family of models, I can question any of those assumptions and come up with 20 different variations on k-means. Okay? I have another demo, but I'm not going to do it so that we can do some other stuff. The demo is basically like the oranges and lemons, but where we can play with the number of clusters, and we can watch it fail occasionally, and so on. It's on my webpage as well. It's called K-means demo or something like that.
What is selection of the initial?
That's also in the demo. So you can play around with different initializations of k-means, and the initialization that I tend to think works quite well is if you initialize your means at random locations of data points. So you pick k data points at random and you put a mean on there, and that way your initialization matches the distribution of the data reasonably well. But you could try other initializations. Okay, so this is a marathon. We did have a break. But now I'm going to do dimensionality reduction really quickly so that we have a few minutes at the end so I can tell you everything I didn't tell you. Okay? So, dimensionality reduction. Again, this was the motivating slide. Data actually often lives in lower dimensions than what's measured. And how many people here know the principal components algorithm? Okay, raise your hand. How many people here don't know the principal components algorithm? Okay, good. That's why we're all in the same room trying to learn lots of common material. Pieces of the... Okay, so principal components analysis is the simplest linear dimensionality reduction algorithm. And so just like all the other examples, I started with a linear method first, so you can get intuitions, and then we can make it nonlinear if we want. So here is the idea. We have n data points, all right? They live in d-dimensional space. Big D could be very large, right? Maybe they're images. They live in million-dimensional space or something like that. That's okay. And basically, for now, I'm going to assume that my data is centered. In other words, I'm going to subtract the mean from the data, because I'm just trying to model the correlations between the different dimensions, how these pixel values might covary or something like that. Okay. And if my data isn't centered, I can easily just compute the average data point, subtract it from all the data, and center it. All right? So, principal components analysis is a linear dimensionality reduction method which finds the linear projections of the data which, and there are 4 different equivalent views of PCA. Okay? They maximize variance, I'll explain that later. They minimize squared reconstruction error, I'll explain that. You can do it with a neural network if you want to inflict pain on yourself. You can do linear dimensionality reduction so that you find dimensions that have highest mutual information with the data under a Gaussian model, or maximum likelihood parameters. Again, note, maximum likelihood, right? So there's a link to a probabilistic model and maximizing some likelihood. under a linear Gaussian function model of the data. These are 4 different equivalent interpretations of PCA, and at least 3 of 2 of them have been around for almost 100 years, and a couple of them have been around for a couple of decades. Okay? So, all right, let's look at the first interpretation. We're going to find a dimension, a projection of the data which maximizes variance. Okay, so what do I mean by a projection of the data? Okay, so remember, I'm just given data points X. I'm going to call W my projection of the data. So W transpose X, let's just do one projection. Okay, the easiest case. W transpose X is a dot product of W and X. Okay, it's mapping my data into some direction, W, and Y is going to be the projection of X onto W. Okay? So we are going to find the W from the data such that the variance of Y is maximized for the data set I observe. And since we've assumed that the data set is 0 mean, the expected value under the data set, the mean of Y, is also 0. Okay, because if I take W times something that has average 0, then the value of that on average will also be 0. Okay? And for every data point, W transpose Xn is going to be the projection of that data point on W, and we're going to call that Yn. So at this point, I'm going to again draw a picture. Okay, so unfortunately, on a board, you can only draw things in 2D. So million dimensions isn't going to work for us. But let's do PCA in 2D. I have some data. It's 0 mean. And my data might let's say look like this. Okay? So now my direction W is going to be my free parameter of the PCA algorithm. And what I want to do is I want to find the direction such that the variance when projected onto W is maximal. Okay? So if I point W this way, what happens to the data when I project them onto W? Projecting is just computing dot products. Okay, so the dot product of the data points with W is what? Large or small? Small. Right, these data points are almost orthogonal, so the dot products are all going to be quite small. They're going to be the distance that the data point goes along this line. Okay, let's do a canonical example. Okay, let's imagine the line is in this direction. Okay, and let's imagine that the length of the line is 1. Okay, the norm of the line is 1. So this is lines on a circle. The projections are just the dot products of projections are how far do the data points fall on this line? And they don't fall very far. Some of them fall positively, some of them fall negatively, so some of these dot products are negative, right? But the variance in this direction is quite small. On the other hand, can I use this green over here? Whiteboard marker, hopefully not permanent. If I point my W in this direction, then my projections of the same data onto this line are quite widely spread. So in this direction, they're spread very widely in the green direction, in the red direction, they're quite narrow, right? And what PCA is trying to do is it's trying to find the direction in the data that's more like the green than the red, okay? That spreads out the data the most. Now, why would that be interesting? This just seems like a bit of silly math. Why would it be interesting? Any ideas?
Because you want to preserve the information for the original.
Yeah, we're trying to find the underlying space that the data lives in. Yeah.
We basically do subspace tracking, track the span over the features. So like we have to have the span that describes more accurately all of our features.
Mm-hmm.
This is basically what we see why we want to.
Yeah, both of those are good answers. So basically, we're trying to find the directions that show the span, what this is the subspace that the data lives on.
In this case, it was a plane.
Yeah. Okay, so let's do this with a bit of math. So basically, I just explained what these W's are. So we're going to maximize the variance of y with respect to W. And the variance of y, because y is zero mean, is just the expected value of y squared, right? The variance is expected value of y squared minus expected value of y quantity squared, 0. So expected value of y squared, which expected value under the data is just the sum over data points of y n squared. That's the cost function for PCA. That's nice. We have cost functions, now we can understand what we're doing a little bit. So let's expand it out. The yn squared expands out to w transpose xn. That's the dot product of w and xn squared. Now, this is a scalar, so we can write it out as w transpose xn. We can also write it out as xn w transpose. These are equivalent. Okay, scalars can be transposed. A little bit of linear algebra we're using here to make our life a little easier. If we know this linear algebra, our expressions become easy. Okay, now this sum over n, we can bring it inside. So we can take the w transpose out, because it doesn't depend on the data points n. We can take this w out, we put some brackets around this whole thing, we bring the 1 over n in, so what we get is w transpose a matrix times w. And that matrix C is actually the data covariance matrix. That is essentially the covariance matrix, in this case a 2 by 2 matrix that you would get if you fit a Gaussian to your data. Okay, so our objective function is to maximize W transpose CW. Now clearly, you can maximize this. If we arbitrarily increase the norm of W, this thing gets bigger and bigger. Okay, if we double W, this thing gets quadrupled, because W appears quadratically. So that's a silly objective function. We need to put constraints on it, and that's why I said, let's assume that the norm of W is 1. So it's going to, we don't want to increase the variance of Y just by increasing the norm of W. We want to restrict ourselves to directions W with unit norm. So we're going to constrain it to be W norm squared, or W transpose W, the length of W to be 1. And now, to solve that problem, we're going to maximize this objective function that we had before, subject to the constraint that W transpose W equals 1. The way we solve optimization subject to constraints is a method called the method of Lagrange multipliers. And I'm not going to go into that because I could spend an hour talking about that, but it's just useful to know that we're optimizing something subject to constraints. The way you do that is you put your constraint down as a function that would equal 0, so W transpose W minus 1 would equal 0 if W transpose W equals 1. So this function equals 0, then you stick a lambda in front of it, and that is called the Lagrange multiplier. And then what we're going to do is we're going to maximize this with respect to W, and we're also going to optimize this with respect to lambda. And when we optimize this with respect to lambda, what we get is that the constraint falls out, right? Take a derivative with respect to lambda, we get this thing. And therefore, the constraint is satisfied when we take that derivative and set it equal to 0. And when we maximize it with respect to lambda, for that, sorry, with respect to W, for that lambda, we solve the constraint optimization problem. That's the method of Lagrange multipliers in, less than a minute explained, okay? So, now, it turns out the solution, W star, of this sort of equation is what's called the eigenvector with maximum eigenvalue of the covariance matrix C. That's sort of a, I probably do this on the next slide, but that's just the answer to this optimization problem. You can solve it analytically, and it's called the eigenvector. And it will find you the direction with maximal variance. Okay? Just as a reminder, again, because people have different kinds of backgrounds, it's useful to have this on one slide. If you have a matrix A, then you can say that lambda is an eigenvalue and z is an eigenvector of A if A times z equals lambda times z. And z is a unit vector, okay? And the interpretation of eigenvalues is that the matrices are operations that you can apply to vectors. And what an eigenvalue tells you is properties of that operation. It says the operation of A in the direction z is simply a rescaling by lambda. That's what an eigenvector is. He's sort of peeking at the way in which the matrix operates on different directions. And the k principal components of a covariance matrix are the k eigenvectors with the largest eigenvalues of that data covariance matrix. Okay, so here's another interpretation where I write down a loss function. I'm not going to derive through this because the answer ends up being the same. I write down a loss function which is a squared loss function between the data and a reconstruction of the data. This is, for those of you interested in neural networks, this is what an autoencoder does. Okay, a linear autoencoder minimizes some loss between the data and a reconstruction of the data, and our reconstruction is going to be in terms of these projections of the data, and we end up with the same cost function. I'm not going to go through this because I want to spend 5 minutes talking about the other stuff. Here's an information theory interpretation of PCA. It's the direction that maximizes the mutual information between x and y. X is the input, y is the projected output. We want to keep the most information about the data in y. And that's difficult to define in general, but if we make some assumptions, if we say, I'm going to assume my data comes from a Gaussian density, okay, then that direction y that maximizes information about the data is the principal components direction. Okay, so we're keeping as much information as possible about the data if the data were assumed to be coming from a Gaussian. Okay, and that's the multivariate version. And here's what happens when you apply it to images of faces. This is kind of nice to look at. This, the first thing, okay, this is, you take a database of pictures of people's faces where they've been aligned. The images have been aligned so that I think like the eyes and roughly the nose and mouth are aligned in these images, okay? And the background is dark. So what's shown here is the mean image. I take my database of 10,000 images or whatever, I take the average of those images, and that's the average face that I get. That's not the principal components. These things are the first, 15 principal components of face space. Okay? In order. So this is the first principal component. What do you think that corresponds to? Skin tone, probably skin tone, some combination of skin tone and illumination. Okay? So these images were taken with different sources of light, and what PCA tells you is that around the mean, that's the center of the data, the direction of most variation in the space of images of faces is overall illumination and possibly skin tone. Okay? What about this second principal component? What does that correspond to? What do you think?
Illumination on forehead.
It's actually probably, it could be hair. It probably is just that maybe the camera, the light angle varied, and some were more shiny on the forehead and some were less shiny on the forehead. Okay? The second principal component seems to be illumination from above, or maybe hair or size of forehead or something like that. The third principal component is telling you left to right illumination. Okay? Right? Dark on one side, light on one side, and so on. And now one of the properties of principal components analysis is that these vectors that come out are all mutually orthogonal. So the kth principal component is going to be perpendicular to the k-1 first principal component. So the principal components are going to get weirder and weirder because they're going to be required to be zero dot product with these other guys. Okay? Now, here is the interesting thing about PCA. If I wanted to reconstruct faces, then probably instead of sending 1,000,000 pixels, I could just send the mean plus, I don't know, the first 30 principal components or something like that, just the weights on the first 30 principal components, and I could probably quite accurately reconstruct most faces in this database. So that's how we could use principal components for data compression, for example. And instead of running my learning algorithm in a 1,000,000-dimensional space, eating up my supercomputer memory or whatever, I could probably run it in my 30-dimensional principal component space. So the practical use case of PCA is that people say, oh, my data is too high dimensional, oh, I can't deal with it. I'm going to do PCA on it, which sometimes is just a crime. You're destroying a lot of information in the data. And then you're like, oh, okay, now my data is 20-dimensional. I can do whatever now on it. Okay? I'm quite unhappy about that. But that is the most common use of PCA. And I'm unhappy because often the data the PCA algorithm is basically making Gaussian assumptions. And if the data you throw into it is text or some weird binary data or whatever, PCA is just the wrong model to use for that. So, but people do it anyway. Okay, so now in exactly the same way as before, if I want to do nonlinear PCA, then the way I can do it is I can take a nonlinear mapping of my data to some feature space phi, and then I can apply PCA in that feature space. And that's called kernel PCA, and it gives you nonlinear projections of the data. Okay? So we are all quite exhausted, I'm sure. 3 hours is a long time, even if you take a break. And so I'm going to spend, unless there are some questions. Are there questions about PCA?
So how did you decide that your 1,000,000 dimensions will be compressed to 50?
Right, it's the same question as the k-means question. How do you decide the number of clusters in k-means? It's the same question as the polynomials question. It's a model selection question. People in PCA, they do some sort of ad hoc methods, like they look at the variance accounted for and they look for a kink in the variance accounted for, or it drops dramatically or something like that. They have heuristics. You can also come up with principled methods for doing this, but that would be the topic of another lecture. Okay. Any other questions? Okay. You guys have 5 minutes literally 5 minutes to hear about some important topics I didn't cover. I think this was pretty well timed, given the title of this lecture. Exactly as planned, I didn't manage to get to this lecture. All right, so what I try to present is just some foundations, okay, basic things. And everything, not everything else, but a lot of other things in machine learning just build on these simple tools like linear regression and kernel methods and, you know, fitting polynomials and logistic regression and k-means and PCA. Okay. So, but there was obviously a lot more to machine learning. And so here is just a list, a very long list of fun things we could talk about if you allow me to give more lectures.
Quite a few more lectures.
But, I mean, I'm happy to do quite a few more lectures. We just should run through the program for this term, and then we'll have lots of time next term, and I'll come in and give lots of lectures. And, you know, I'm happy to have those arranged. So, here's a very long list of possible things that we could talk about. So, somebody asked about semi-supervised learning, combining supervised and unsupervised learning. There's the whole probabilistic modeling and Bayesian machine learning framework that I do a lot of research on, and I could try to explain that in an hour or two. There is reinforcement learning, a really important topic, and its relationship to bandit algorithms. So this is like you know, multi-arm bandits and things like that. Its relationship to Bayesian optimization, another very interesting topic. All these things are related. There is kernel methods. So support vector machines, widely used until neural nets tried to kill them. Well, they first tried to kill neural nets, and then neural nets came back and are trying to kill them. But still very useful to know about, very widely used. And the Bayesian version of support vector machines, which is Gaussian processes, essentially, Bayesian kernel methods. There is neural nets, and they're rebranding into deep learning. Okay. Optimization methods. You're going to have whole lectures on optimization methods. Have you had them yet, or no? Not yet. But I'm hoping that your lectures will cover topics like convex optimization, extremely widely used in machine learning. Stochastic gradient descent, adaptive learning rates, probably less likely to be covered in optimization lectures, but still interesting. Graphical models. Again, I think I have like 4 or 5 lectures on this topic. Learning theory. Learning theory tells us how to measure the predicted performance of a learning algorithm on future data. How to predict how well it's going to do on future data with bounds. So usually learning theory gives us bounds on predicted performance on held out data. Inference algorithms, things like MCMC, sequential Monte Carlo, variational methods. Big topic in machine learning, decision trees and random forests. So almost every machine learning competition, if it's not won by a deep learning method, it's usually won by a random forest. Okay? And often, you know, often one beats the other dramatically. Deep learning methods seem to be quite good when you have massive amounts of data and it's vision data or something like that. Random forests when you're just trying to learn from features that you couldn't stick into a convolutional neural network in a sensible sort of way. We have time series models, things like hidden Markov models, state space models, recurrent networks, etc. We have probabilistic programming, one of the sort of interesting research themes in the Alan Turing Institute. So that's a very long list of things, and I provided a bunch of slides that cover some of this material, but you know, this is meant like an appendix to the lectures I just gave, and you know, consider this reference material. At the end of this, there is if you're interested in probabilistic machine learning, which is kind of the area that I mostly work in, there is a review article called Probabilistic Machine Learning and Artificial Intelligence, which I also provided in the materials, which is written for a general science audience. So, you know, it should be fairly accessible. All right, so that's it. I'm done.